okay, in the previous lecture we have seen that your what you call the frequency versus power output or valve or gate position, right. This we have explained in the previous class. Now, your load sharing by parallel generating units. Now, that was for a single generator. Now, if two or more generating units, right, with drooping governor characteristics, right, are connected to a power system, this must be unique frequency at which they will share a load change, right. So, figure 7 that I will show you later shows the droop characteristic of two generating units. Initially, they are operating at nominal frequency f0 with outputs Pg1 and Pg2. I will show you the diagram. An increase in load delta PL causes the generating units to slow down and the governor increase the your what you call output, right. So, just hold on. So, in this case, so until they reach a new common operating frequency, the FC, right. FC is the common frequency. Now, this is your FC. Now, you see that two generating units are there. This is a generating unit 1 and this is generating unit 2, right. So, let me increase the your just hold on. So, now, these two generating units are there. This is your one is Pg1, another is Pg2, right. So, if you look into that when this has a different droop characteristic, this has different droop characteristic, right. When they are operating at say nominal system frequency, they say f0, right. So, at that time generator 1 was delivering power Pg1, right. This is Pg1, and if you draw a horizontal line, another one at that time was developing power, generating power Pg2, right. Now, the load has increased. If load has increased, so now because of that Pg1 has increased to your Pg1 dash and Pg2 now it is Pg2 dash. So, load has increased, so power also from the two generating generators they have also increased. So, in that case they have to operate at common frequency. This is Fc is the common frequency, this is the common frequency Fc, right. So, if you draw a horizontal line at that time, this one is Pg1 dash and this one is Pg2 dash, right, unless and until and their droop slope that are that is droop characteristics are different, but common frequency the deviation that is your delta f, right. That means that means this is delta Pg1 and this is delta Pg2. Delta Pg1 means Pg1 later I have given it is Pg1 dash minus Pg1, right. Similarly, delta Pg2 this one is equal to your Pg2 dash minus Pg2, right. So, if we write down those delta f by your what you call R is equal to that delta Pg1 I told you Pg1 dash minus Pg is equal to delta f upon R1, right, because frequency deviation is common. This is equation 2. Similarly, delta Pg2 will be Pg2 dash minus Pg2 to delta f upon R2, right. Now, if you divide equation 2 by 3, then you will get delta Pg1 upon delta Pg2 is equal to R2 by R1, that according to this ratio the power will be shared for two generating units, but if R1 is equal to R2, if their droop characteristic same, then delta Pg1 will be equal to delta Pg2, right. So, if the percent regulation of the units are nearly equal, that means if R1 is equal to R2, the change in the outputs of each generating unit will be nearly in proportion to its rating, right. So, if it is R1 if it is R2 is equal to R1, then delta Pg1 will be equal to delta Pg2, right. So, this is how that your what you call that meaning of droop characteristic, that why do we need that for governor, it is more or less clear to us, right. Now, control of power output of generating units. So, the relationship between frequency and load can be adjusted by changing an input shown as load reference set point, that is u, right. This is actually load reference set. I will come to the diagram, that is figure 7, right, as a load reference set point u, right. So, this is actually same block diagram, but only that your one additional feedback is here, that is called load reference set point, that is called u. Rest all the things same as before. So, the schematic diagram, governor and turbine, right. Now, if this u is there in the previous diagram, when we reduce this one, it was like this. No, now this u is added, right. In the previous diagram, it was your what you call that we make it, this is your minus 1 upon r, this was delta f, and this one is 1 upon 1 plus s t g, and this is delta E s, right, or delta E. Now, as this u has been added here, right, that is load reference set point. So, this block diagram actually it is minus 1 upon r, it is this, because of this minus 1 upon r, this minus feedback is here, 1 upon r is here, this is delta f and this is u, right. So, if you just or what you call go for block diagram reduction, then this you will get this one, only this u will be added here, right. So, that u feedback will be there, the load reference set point. So, this is the meaning of this one, actually this is reduced block diagram for governor. Now, so from the practical point of view, the adjustment of load reference set point is accomplished by opening the speed changer motor, right. This speed changer motor we will not see in this course, but this is the your what you call, this is required. So, figure 8 shows the effect of this adjustment, that family of characteristics are shown in figure 8, that I will show you for different speed changer motor setting, right. Now, if you come to this figure, that there are 3 different characteristics, there are 3, just let me move it little bit up, 3 different characteristics. So, if you look into this, that this is figure 8, effect of speed changer setting governor characteristic. Now, characteristic A, characteristic B and characteristic C, right. Now, when it is operating at nominal system frequency, say it is 50 hertz, right. So, power generating is 0 for this one, but at the same time your what you call, if it is operating at 50 hertz, then for B it is 50%, right, and for C it is, because look at this dash line, it is 100%, say for a change of your what you call that 6% your droop value, that is your 6% change in frequency, right, that is your nothing but your 3 hertz, because 6% means 0.06 into 50, if 50 hertz system. So, this drop is 3 hertz. So, although they have different characteristics, so from that you can see that this is a simple simple example, right. So, let me clear it. So, we will go to the next one, right. So, the characteristic whatever we have seen, right, if necessary I will go to that the characteristic that whatever we saw, that your figure 8, that 3 different characters associated with 50 hertz, these characteristics are shown representing 3 load reference setting, that I told you. So, at 50 hertz characteristic A results 0 output, I told you, characteristic B result 50% output and characteristic C result 100% output. Therefore, by adjusting the load reference setting U through activation of the speed changer motor, the power output of the generating unit at a given speed may be adjusted, right. So, later we will see little bit more about that. To any desired value for each setting, the speed load or what you call characteristic has a 6% droop, right. So, that is a speed change of 6%, that is 3 hertz, causes a 100% change in power output. This we have seen before, right. So, next is your what you call that after this. So, governor part more or less over. Next we will go for turbine model. So, in this course we will see only that steam turbine model. If time permits, at the end of this course, if time permits, then little bit of hydro turbine modeling I will give you, very interesting it is. First we will finish this in steam turbine model, right. So, all compound steam turbine system utilize governor control valves at the inlet to the high pressure or very high pressure, right. Turbine, I mean just bracket we are putting the turbine to control the steam flow, the steam chest and inlet piping to the steam turbine cylinder and reheaters and crossover piping down your downstream all introduce delays between the valve movement and change in steam flow. That means, you have actually in a details so cannot be covered in this course, right. So, question is that for it is a reheat type turbine, it has high pressure, intermediate pressure and low pressure cylinders are there, right. So, steam chest and inlet piping and everything, that when steam is flowing, everything is associated with delays, some time delay, that will represent by time constant, right. The steam chest and inlet piping to the steam turbine cylinder and reheaters and crossover piping downstream all introduce delays between the valve movement and change in steam flow. The mathematical model of the steam turbine accounts for these delays, right. So, now figure 9, before coming to this thing, I will go to figure 9 first, then we will be coming back to that, right. So, when you see figure 9, that it is your tandem compound, that your steam turbine. So, valve position like this, that control valve steam chest. So, reheater is there, then it is high pressure cylinder, then intermediate pressure cylinder IP and then low pressure LP, right, and this is crossover and this is the shaft, and from here it is going to condenser, right. So, everywhere when steam is flowing from this part to that part, some delay is associated with that, right. Now, before going to that, this is steam system called tandem compound single reheat steam turbine, right. So, now everywhere when that is your delta ES, that is because governor, then turbine, then your generator all are connected together, turbine generator coupled together. So, input here is delta ES, right. So, this is 1 upon 1 plus STT, that is steam chest time constant, then power developed in the high pressure side, say FHP, the fraction of power, then intermediate pressure it is FIP, and low your what you call low pressure cylinder, that is developed FLP, right. So, FHP when we put in per unit, that FHP plus FIP plus FLP, that is actually is equal to 1.0, right. So, these three if you sum it up, it is 1.0. Now, or we can write that FIP plus FLP is equal to 1 minus FHP, right, from this equation only. Now, this crossover, this TC, this the time constant, that is your what you call, it is very small, right, that crossover. So, this time constant is neglected. If you neglect this, if this is neglected, then it will be FIP plus FLP together, FIP plus, and this is delta PG. Now, FIP plus FLP actually is equal to 1 minus FHP, right. This is I am telling. Now, we will go to the that mathematical model development, that transfer function model, right. Now, if you now when we will go up now, so just hold on, yes. So, figure, that is figure 9a I showed you, shows a schematic diagram of a tandem compound single reheat steam turbine, and 9b shows the linear transfer function, that also showed model of the tandem compound single reheat steam turbine. The time constant TT, TR and TC represent delays due to steam chest. TT is steam chest and inlet piping time constant, TR is the we call reheat time constant, and TC we call crossover piping, that is the time constant, this crossover time constant, right. the fraction FHP, FIP and your FLP, right, represent portions of the total turbine power developed in the high pressure, intermediate pressure and your low pressure cylinders of the turbine, right. So, it may be noted that FHP I told you plus FIP plus FLP is equal to 1.0, right. So, high pressure, low pressure, intermediate pressure and low pressure. The time delay in the crossover piping TC I told you being very small as compared to other time constant is neglected. So, TC for this thing is neglected, we will not consider TC, we will simplify it, right. Therefore, the reduced order transfer function model is given in figure 9C. So, we will go the portion of the total power generated, that is figure 9C also I showed you already, just we will go once again, right. So, this is figure 9B or 9C, though this one TC is neglected, though figure 9C will be your this one, the reduced order model. So, TC is neglected, it will be 1 upon 1 plus STT, this is FHP, 1 upon 1 plus STR, TC is neglected and FIP plus FLP is equal to 1 minus FHP. So, this is 1 minus FHP and output is delta PG, right. So, this is that diagram. Now, from there we will try to find out delta PG upon delta E, that is your simply transfer function. So, we will go up. So, from figure C, right. So, you can write delta PG is equal to from figure that 9C is equal to 1 upon 1 plus STT into FHP plus 1 minus FHP upon 1 plus STR into delta ES. This is you go to figure 9.6 and easily you can write this, right. Or after simplification, delta PG upon delta E, S is Laplace your what you call operator. So, is equal to 1 plus S KRTR upon 1 plus STT into 1 plus STR. Here one small question to you, that when you find out that your what you call this transfer function, right. So, what is KR? KR is equal to here what? Here only FHP is there. So, KR is what in terms of HP? This is a small question to you. So, KR we call reheat coefficient, right, that we call KR, that is. So, KR is reheat coefficient, that is the function of the power, fraction of the power generated in the high pressure cylinder. So, basically KR is equal to what, as fraction of power generated in high pressure cylinder means KR is equal to what, a small question to you, right. So, but generally we call KR as a reheat coefficient. So, this is equation 5. So, this is the transfer function for the your reheat turbine, right. And if it is a non-reheat turbine, right, suppose this is reheat turbine, if it is a non-reheat turbine, right, then you have to, then there will be no existence of TR. So, TR should be is equal to then 0, right, if it is a non-reheat. That means, in that case for non-reheat turbine, the transfer function should be basically simply 1 plus STT, that is equal to this one for non-reheat turbine, right. So, for here I have written here that for non-reheat turbine, the delta PG upon delta E is equal to 1 upon 1 plus STT, right. So, here actually here FHP is 1, that means for this equation, right, if you take actually KR is equal to FHP, right, and that is equal to 1. So, because reheater is not present. So, in that case if you put KR is equal to 1, that means your 1 plus STR will be cancelled, or as reheater is not there, you can simply put TR is equal to 0, then it will be 1 upon 1, the way you want, right. So, these figures, all these things have been told and explained, right. So, now we have to now complete that your next model is, next one is that your generator load model, right. So, this is actually generator to load model. So, increment in power input to the generator generated load system is delta Pg minus delta PL, right. So, idea is something like this, it is a lossless turbine. So, we could assume delta Pg is equal to delta PT, right, and if load there is a load changes, then there will be transient imbalance between the generation and the load. So, what will happen that whatever load changes, generation will try to follow that load. If load increases, generation will try to generate that amount of power, right. So, but as soon as you switch on the load, a transient imbalance will happen, right. So, it is not the steady state, first we have to see the dynamics, the transient imbalance will happen. So, incremental turbine power, this is output, right. Incremental turbine power output, assuming generator incremental loss is negligible, I mean it is a lossless turbine, right, and delta PL is the load increment, that is small perturbation, and delta Pg minus delta PL is accounted for in two different ways. So, we have to consider both. Now, that first one is the rate of increase of stored kinetic energy in the generator rotor, right. So, at scheduled system frequency, that is F0, the store energy WK0 will be H into PR megawatt second. This you have studied from your transient stability also, right, because inertia of the machine is H, that is in second, and PR, the rated capacity of the machine turbo generator system, that is your in megawatt. So, its unit is megawatt second. So, this is equation 7, where PR is given that rated capacity of turbo generator megawatt and H is inertia constant, that is actually in second, right. So, initial your what you call store energy, that is WK0 is equal to H into PR. Now, the kinetic energy actually is proportional to the square of the speed. We know that kinetic energy is proportional to the square of the speed, and hence the frequency, right, because you know that omega is equal to 2 pi f. So, that is the kinetic energy at a frequency, say F0 plus delta F is given by, because load has changed. So, initially the frequency was F0, right. Now, suddenly load has changed. So, frequency has changed, instead of F0 now it will be F0 plus delta F. So, delta F that much change is there. Therefore, that because of that, as the kinetic energy is proportional to the square of the speed, therefore, WKE is equal to WKE0 into F0 plus delta F upon F0 whole square, right. So, directly you can write. So, then WKE0, that your WKE0 is equal to HPR, right, that we have made it approximately, and if you expand this one, this is actually F0 square plus 2 F0 delta F plus delta F square, right, divided by F0 square, right. This one you can write 1 plus 2 delta F upon F0 plus delta F upon F0 square, right. But this delta F upon F0 square is a very small quantity. So, this term is dropped. Therefore, this equation is written 1 plus 2 into delta F upon F0, right, when you are dividing it by this thing. So, this term is dropped, or and you know that rate of change of kinetic energy is power, then you take the derivative with respect to time. If you do so, it will be 2 HPR, right, divided by F0 into ddt of delta F, right. So, this is equation 8. So, because this is kinetic energy and we are taking your derivative. So, rate of change of kinetic energy is the power, right. This is your equation 8. Now, next is that it is assumed that the change in motor load is sensitive to the your what you call frequency variation. However, for small changes in system frequency delta F, the rate of change of load with respect to frequency, that is delta PD delta F. Sometimes we write if load disturbance is PD, then it is delta PD delta F. If you assume load disturbance is PL instead of PD, then it will be delta PL delta F, right. So, can be regarded as constant. So, these load changes can be expressed as delta PL delta F into your delta F, but this is actually, this one actually is a constant, this is constant, right. So, this part is a constant into delta F, we call this is d into delta F, right. Therefore, that the power balance equation can be, because transient imbalance has happened because of change in load. So, delta Pg minus delta PL can be written as now that 2H PR upon F0 d dt of delta F, that is your d dt of WKE, right. So, that is actually 2H PR upon F0 d dt, this we have seen, plus this term d into delta F, right. Now, both side what you do, both side you divide by PR, both side you divide by PR. So, this is delta Pg upon PR minus delta PL upon PR is equal to 2H upon F0 d dt of delta F, then d upon PR into delta F. That means, both sides it is divided by PR, that is the rated capacity. That means, this is becoming your delta Pg in per unit, that is why in bracket it is per unit written, minus delta PL per unit, then 2H upon F0 d dt of delta F, right, plus d also in per unit it will be Pu, because it is your delta PD upon delta F. So, d also represent by your d in Pu and into delta F, right. But this delta F actually it is in hertz, right. But if you bring this F0 inside that 2H d dt then of delta F upon F0, then in that case it will become per unit, but this thing also you have to take care of, you have to consider that, right. So, better we should not do that, but delta F everything is in per unit, but delta F is in hertz, right. F0 also is in hertz. So, thank you very much, we will be back again.